Let's take a look at another sample here. We have a half a mole of an ideal gas, and we're going to start it at state A, take it through a cycle to state C, then D, then B, and then back to A, and we'll take a look at a variety of the values of the gas during that process. First thing we're going to look at is the change in the internal energy. Since it starts at position A and it goes through the cycle C to D to B and back to A, its internal energy change is 0. Similar to displacement, since I start and end at the same place, the change is 0. Next, we're going to take a look at the work done on the gas during the process. Start at A and go to C. As we go from A to C, our change in volume is 0. So work from A to C is 0. If we take a look at our cycle, we also see a vertical line from B to D. Single volume, no volume change, and so our work from D to B is also 0. From C to D, we do have a change in volume, so we can find the work there. Our pressure at that point is 0.5 times 10 to the 5th pascals. Our change in volume is going from 10 to 30 times 10 to the minus 3 meters cubed. So our volume is increasing. So final minus initial, 30 minus 10 times 10 to the minus 3 meters cubed. So the work we have from C to D is 1,000 joules. And the gas volume is increasing, so that is work done by the gas. The other place we have work going on is from B to A, returning to our original spot. Our pressure at that point is 1.5 times 10 to the 5th pascals. And our volume changes the same, only now it's in reverse, so it's going to be 10 minus 30. So our work here is negative 3,000 joules. Since it's negative, since the volume is decreasing, this is work done on the gas. So our net work is the sum of all those, so we end up with 1,000 minus 3,000. So we have negative 2,000 joules of work done. Heat added to the gas during the process. Well, we found from part A that the change in internal energy is 0, and internal energy change equals Q minus W. So we have 0 equals Q minus W, which means that Q, heat, equals the work done. Well, the work done is minus 2,000 joules, so that means that Q is negative 2,000 joules. So heat is not added. We have a negative Q, so heat is removed. Now we're looking for the temperature at point C if the temperature at point D is 3,000 Kelvin. So C and D have constant pressure. Our volume is changing. If we take a look at the combined gas law, we have P1 times V1 over T1 equals P2 times V2 over T2. Pressure is constant because we're going on along a horizontal line, so we have volume 1 over T1 equals V2 over T2. Okay, we're going to be given quantities starting with D, so our volume at D is 0.030 meters cubed. Temperature is 300 Kelvin. At C, we have a volume of 0.010 meters cubed, and we're looking for T2. And we find that T2 is 100 Kelvin. And that takes us through this example of heat cycles.